Module 1, Occurrence and Impact of Disasters. Unit 1, Point 2, Occurrence and Impact of Landslides. Learning Outcomes. At the end of this unit, participants will be able to identify areas prone to landslides and understand the methods used to assess these risks. They will also be able to explain the general causes of landslides, distinguish between different types of landslides, and evaluate their environmental, social, and economic impacts. These learning outcomes provide a holistic approach to comprehensively understanding landslide hazards. Landslide definition. Landslides are natural phenomena in which a mass of soil or rock on a slope moves downward under the influence of various factors. Rainfall, earthquakes, ground saturation, or other triggers can initiate this movement. Although gravity is the main driving force, the stability of a slope depends on many factors such as the type and strength of the material, lithological structure, hydrogeological conditions, slope angle, seismic activity, and meteorological conditions. Therefore, the stability of a slope is a dynamic state of balance shaped by the interaction of different natural processes. General causes of landslides. Multiple natural and environmental processes play a role in the occurrence of landslides. Climate change and rising temperatures significantly increase landslide risk, especially in mountainous regions covered with snow and ice. The thawing of permafrost weakens the integrity of rock slopes, leading to instability and increasing the likelihood of movement. In addition, events such as intense rainfall, periods of drought, earthquakes, and volcanic activity are among the key factors that can trigger landslides. Some areas are more sensitive due to their natural conditions. Steep slopes, canyon floors, areas previously affected by wildfires, or regions disturbed by human activities are examples of this. In areas with intense surface runoff or highly saturated ground, the risk becomes even higher. General causes of landslides. Landslide formation results from the combined influence of geological, morphological, and human-induced processes. From a geological perspective, the presence of weak or sensitive materials, the weathering of rocks and soils, and the development of sheared, jointed, or fissured structures increase landslide risk. Adverse orientation of discontinuities such as bedding planes, schistosity, fault zones, or unconformities can also undermine slope stability. Differences in permeability or stiffness between materials affect water flow and stress distribution, thereby weakening stability. Morphological factors also shape this process significantly. Tectonic or volcanic uplift, the retreat of glaciers, or erosion by rivers, waves, or glaciers can weaken slopes from their base or sides. Subsurface erosion, loading at the crest due to deposition, the loss of vegetation through fire or drought, and freeze-thaw cycles are other important processes that destabilize slopes. Human activities can greatly increase landslide hazard. Excavation at the slope face or toe, unplanned loading, rapid drawdown in reservoirs, deforestation, and intensive irrigation all raise these risks. Mining operations, artificial vibrations, and leakage from infrastructure change ground behavior and further increase the likelihood of landslides. Classification of landslides. Landslides are classified into different groups according to their mode of movement. The first group, falls, is characterized by the free fall of rock or soil masses. Topple occurs when a mass rotates forward around a pivot point and tips over. Within the slides category, there are two main subtypes. Rotational slides involve movement along a concave curved surface. Translational slides occur along a flatter sliding surface, with the mass generally moving as a more coherent block. Spreads develop through horizontal deformation that extends over wide areas when the ground structure collapses or loses strength. The final group, flows, forms when the material becomes saturated with water and begins to behave like a fluid. Within this category, there are different flow types, such as debris flow, debris avalanche, and earth flow. Rockfall. Rockfall is a type of landslide typically observed on steep or nearly vertical slopes. The size of the detached material can vary widely, ranging from small rock fragments to large blocks with volumes of thousands of cubic meters. Natural processes play a major role in the formation of rockfalls. River undercutting, slope steepening, and differential weathering can all disrupt slope integrity. In addition, human activities such as road construction can weaken the base of a slope and accelerate this process. Earthquakes and strong vibrations can further destabilize already fragile slopes and trigger rockfalls. Topple. Topple is a specific type of landslide in which a mass rotates forward around an axis and overturns. This type of movement is frequently observed along steep slopes, in volcanic regions, and along riverbanks. Topple events can be triggered by several factors. The gravitational force exerted by material located upslope is the main driver initiating the overturning motion. Water or ice penetrating cracks within the rock mass further weakens the structure and increases the risk of toppling. Vibrations, river erosion, excavation works, weathering processes, and other environmental effects can also contribute to the occurrence of topples. Rotational slides. Rotational slide is one of the most common types of landslides, especially in fill materials. This type of movement occurs primarily in structurally homogeneous soils and is typically associated with slopes between 20 and 40 degrees. During movement, the ground mass rotates and slides downward along a circular or concave surface. Such landslides are often triggered by intense rainfall, rapid snowmelt, or sudden changes in groundwater levels. Saturation of the soil weakens the sliding surface and increases the risk of failure. Earthquakes can also disturb the existing stress balance and accelerate the development of rotational slides. Translational slides. Translational slide is one of the most widespread types of landslides worldwide and is generally shallower than rotational slides. In this type of movement, the mass slides downslope more or less as a coherent block along a relatively planar surface. The ratio of the sliding surface thickness to its length is small, and the scale of the event can range from failures affecting small residential areas to large regional landslides extending for kilometers. Translational slides are most commonly triggered by water-related processes such as intense rainfall, sudden rises in groundwater level, snowmelt, flooding, irrigation, or water leakage. Human activities such as undercutting or removing support at the base of slopes also play an important role in their formation. Earthquakes, of course, can also disturb the equilibrium along the sliding surface and initiate translational movement. Now, quiz time. Landslides can occur in conjunction with heavy rainfall, drought, earthquakes, or volcanic eruptions. True or false? Correct answer, true. Spreads. Spreads are a type of landslide that occurs worldwide, particularly in regions with soils susceptible to liquefaction. These movements are often associated with seismic activity, but they are not confined to seismically active areas only. Initially, only a few small cracks may appear in the ground. However, these cracks can rapidly widen and propagate, developing into a spreading movement that affects areas hundreds of meters across. Triggers that destabilize the weak underlying layer include liquefaction caused by earthquake shaking, natural or human-induced loading of an unstable slope, and saturation of the weaker layer due to intense precipitation, snowmelt, or changes in groundwater levels. Liquefaction of sensitive marine clay following erosion at a riverbank or slope base, and plastic deformation of weak deep-seated materials also accelerate this process. Flows. Flows are another major category of landslide movement. Debris flows are widespread and often occur in steep gullies and canyons. They can be intensified when slopes lose their vegetation due to wildfires or logging. Volcanic regions with weak soil commonly experience such flows as well. Their thickness varies. They may be thin and watery or thick with sediment and debris, and they usually remain confined within the steep gullies that control their movement. These flows are generally shallow but have long, narrow runouts that can extend for kilometers in steep terrain. A debris avalanche is the very rapid to extremely rapid form of a debris flow. Debris flows often result from intense surface water flow caused by heavy rainfall or rapid snowmelt. This flow erodes and mobilizes loose soil or rock on steep slopes. Debris flows can also originate from other types of landslides on saturated slopes, involving significant amounts of silt and sand-sized material. Earth flows. Earth flows are flow-type landslides that commonly display a shape resembling an hourglass. In these movements, material on the slope becomes saturated with water, almost turning into a liquid mass. It then flows downslope, creating a concave or sunken area at the upper part of the slope. Earth flows typically occur in fine-grained soils or rocks containing clay. They develop on moderate slopes and are strongly associated with fully saturated ground conditions. Tilted trees, bent fences, and ripple-like patterns on the ground surface are characteristic field indicators of earth flows. Landslides, real cases. This slide shows real-world examples of different types of landslides. The image on the left illustrates a spread-type failure, where weak underlying layers suddenly extend laterally. The separation of the road surface into large blocks is a typical feature of this type. Just below it, there is an example of debris flow, where a thick mixed mass flows downslope and impacts residential areas. These flows often follow intense rainfall or sudden water surges and transport a large volume of debris. The central photograph presents an earth flow. The saturated fine-grained soil mass moves slowly but noticeably downslope, leaving behind a long distinct flow path. The upper right image shows a rockfall. Rocks detach and fall freely from a steep slope, a process that severely affects roads and transportation routes. Finally, the lower right image depicts a topple-type landslide where the mass rotates and tips forward. This type is common along steep, highly fractured rock faces. Environmental impact of landslides. This section presents the impacts of landslides on the natural environment. Landslides first affect the shape and structure of the Earth's surface, directly altering topography. Large mass movements can reshape valleys or create new depressions. They also have distinct effects on water systems. River courses may change, water quality may deteriorate, and groundwater circulation can be disrupted. Forested areas are significantly damaged by landslides as well. The loss of vegetation can lead to long-term degradation of ecosystems. Finally, the habitats of many different species are affected by these processes. The living environments of organisms inhabiting rivers, lakes, and coastal ecosystems may change or be destroyed as a result of mass movements. These impacts show that landslides are not only geological events, but also major environmental threats. Environmental impact of landslides. Landslides do not only generate direct impacts, they can also trigger secondary hazards. This is especially true for landslides that occur after earthquakes, floods, or volcanic eruptions, which significantly increase environmental risks. Earthquake-induced landslides can cause dangerous tsunamis when large volumes of material plunge into bodies of water, displacing a significant amount of water. Landslides resulting from volcanic eruptions or earthquakes can obstruct river channels, leading to water accumulation upstream, and in some cases, the formation of natural dams. If such a dam fails, the stored water can be released suddenly and cause severe flooding downstream. These floods may have far-reaching consequences, including the erosion and destabilization of riverbanks and coastal areas, rapid saturation of slopes, and undercutting of cliffs and bluffs. Therefore, the secondary hazards triggered by landslides are at least as critical as their direct effects. Social impacts of landslides. Landslides do not only cause physical damage, they also leave deep marks on the social fabric of communities. The collective trauma experienced by a community can weaken social bonds and disrupt social cohesion. For this reason, psychosocial support, counseling services, and community-based solidarity programs are of vital importance. The social impacts of landslides can also lead to political consequences. Risk management policies, land use decisions, and disaster preparedness processes may be reshaped under public pressure and social expectations. Raising awareness, establishing effective early warning systems, improving land use planning, and involving communities in decision-making are critical steps in reducing social vulnerabilities. When these measures are prioritized, societies become more resilient and better prepared for future landslides and other natural hazards. Quiz time. Which one of them is not among the types of landslides? A. Flows. B. Topple. C. Falls. D. Spreads. E. Coastal. Correct answer, coastal. Economic impacts of landslides. Landslides cause large-scale and multidimensional economic losses. Residential areas built on unstable slopes may experience damage ranging from partial to complete destruction. This affects not only buildings, but also walls, roads, utility networks, and all above-ground and underground services. Sometimes the impact of a landslide is limited to a single structure. In other cases, it can encompass an entire neighborhood. Fast-moving types such as debris flows pose the greatest threat to structures due to their high velocity and strong destructive power. These events often occur suddenly and without warning, making the implementation of preventive measures difficult. Settlements located on steep slopes are particularly vulnerable to debris avalanches and lahars, which can severely damage cities, towns, and infrastructure. Failures along roads and railways, including cut-and-fill failures or collapses in weak slide-prone soils, disrupt transportation networks. Rockfall events can also directly harm individuals and infrastructure. Catastrophic historical landslide disasters. Throughout history, many large-scale landslide disasters have occurred, affecting the lives of thousands of people. In 1963, the Vajont Dam disaster in Italy was triggered by the massive sliding of a mountainside into the reservoir, generating a large tsunami in the dam lake and causing the deaths of around 2,000 people. In 1966, the Aberfan disaster in Wales occurred when a coal waste tip collapsed and buried a school and nearby houses. A total of 144 people, most of them children, lost their lives. In 1985, the Armero tragedy in Colombia was caused by a lahar triggered by the Nevado del Ruiz volcano, resulting in the deaths of more than 25,000 people. In 2007, the Chittagong landslides in Bangladesh were triggered by intense monsoon rains, leading to hundreds of deaths and the displacement of thousands. In 2010, a massive landslide in the Zhouk region of China caused the deaths of more than 1,400 people and inflicted severe damage on infrastructure. In 2017, a major landslide in Sierra Leone led to hundreds of fatalities and widespread destruction. Also in 2017, the Mocoa landslide in Colombia occurred after intense rainfall and resulted in the deaths of more than 300 people. These events demonstrate that landslides are not merely natural processes, but major disasters that profoundly affect societies. Before moving on to the next unit, here is a short self-assessment test about the occurrence and impacts of landslides. It includes 5 questions and helps you see which topics you already understand and which ones may need more focus.